Let's now try to understand why this algorithm works. That is, what is the guarantee that the shortest path tree that it will produce at the end genuinely reflects the shortest paths from the source to each vertex in that tree? Well, at the beginning of the algorithm, we clearly know that S is at distance 0 from itself. So clearly when we start out, the shortest path tree, which only has S in it, clearly reflects the correct shortest path distance value to itself. We also know that if S has a bunch of neighbors, then the lowest cost edge connecting S to its neighbors will identify the closest neighbor, because the closest neighbor must be a one-hop neighbor, and so whichever edge has the lowest weight in it out of S, that is going to lead us to capturing the closest neighbor of S. So let's assume that after I iterations, the algorithm will correctly capture the I closest neighbors of S. So I'm trying to come up with a proof here by induction, and our induction hypothesis is that up to the ith iteration, let's say that we correctly capture all the closest neighbors of S one by one in increasing order of distance, so that the first I neighbors have been captured by the end of the ith iteration. So on the left side then, in the captured set, I'm going to have a bunch of values associated with each of those captured neighbors, which reflect their final and true shortest path distances from S. This is the assumption that at least up to the ith iteration, everything has gone smoothly and correctly. The question is, can we prove that the I plus first iteration will correctly capture the I plus first closest neighbor of S? If we can prove that, then that means we have a proof that can generalize from any I to I plus 1, which means that if we have our base case covered, which we do because we said that when the algorithm begins in the at the very beginning as well as after the first iteration, we do have the closest neighbor of S calculated correctly, and if we can go from I to I plus 1, that means we can go from 1 to 2, we can go from 2 to 3, we can go from 3 to 4, and so we can generalize and say that after any number of iterations we will correctly have the corresponding number of closest neighbors correctly computed and added to the growing shortest path tree. Now suppose we look at the shortest path to the I plus first closest neighbor hypothetically. Hypothetically, we imagine laying down the shortest path to the I plus first closest neighbor, which is basically this node. Then it must be the case that all the preceding vertices along that path, and those are these vertices, all these vertices must have a rank of less than or equal to I as far as their proximity from S is concerned. So these must all belong to the set of I closest neighbors, and this in turn means that they must all have been captured and added to the growing shortest path tree during those I iterations. So after I iterations are over, all of these vertices must already exist in the partition on the left hand side. They must already have been captured. So if I were to represent them in our partitioning diagram, in the captured set they must all be present, and so we'll find them on the left hand side. Now if we look at that final edge which leads up to the I plus first closest neighbor, this last green edge, how will that green edge appear in the diagram that we just drew? Well, that green edge is going to show up as an edge across the cut. So the I plus first closest neighbor must be lying at that point on the right hand side, and because there is a cut edge to it, when we had captured this vertex, whatever that was, and looked at its adjacency list, we would have discovered the I plus first closest neighbor if it wasn't already discovered. So this is the I plus first closest neighbor, I'm assuming, and we have a cut edge leading across to it. Now the shortest path distance value on this particular vertex is the true value. That is our induction hypothesis, that we have the true shortest path distance label existing on this vertex. So when we looked at the adjacency list of that vertex and we saw this cut edge going across to the I plus first closest neighbor, we would have scheduled a particular time at which the I plus first closest neighbor is going to be infected. And what would that time have been? That time would have been this true value plus the weight of this cut edge, and that must be the time associated with the I plus first closest neighbor. It might have had some other time initially if it was already discovered, but at least we know there is no shorter path to it from anywhere on the left hand side, because we were looking at the shortest path already and we said this cut edge is the last edge on that shortest path. So when we look at that cut edge, we are going to set the actual shortest path distance to that I plus first closest neighbor at that moment. Now what about the labels on the other vertices? What labels would they have? Is it possible that any of them could have labels that are smaller than this value that we just set on the I plus first closest neighbor? Well, the answer is no, because if there was a label, suppose there was a label here, let's say L, which was smaller than the value on the I plus first closest neighbor, that means there must be a cut edge into it which would have led us to put this value. And if there was a cut edge like that, then the vertex that it came from must also have a true value, a true shortest path distance value on it, which when added to the weight of this cut edge would have led to a value that's equal to L. But if L is less than the value that we put on the I plus first closest neighbor, then it means there is a path to this yellow vertex whose length is smaller than the shortest path distance to the I plus first closest neighbor. And if that's the case, then the I plus first closest neighbor must be this vertex and not the vertex that we were given as the I plus first closest neighbor. So we end up at a contradiction. We assume that we were given the actual I plus first closest neighbor and we were given the shortest path to it, and so it must be impossible to find any such vertex elsewhere with a smaller label than what we have over here. Now, having proven this, our algorithm will in the next step naturally extract the vertex with the minimum value for the priority from that priority queue data structure, and when it does so, it's going to capture the I plus first closest neighbor. So that means after the I plus first iteration, we're actually going to have the I plus first closest neighbor captured. And so we have proven that our algorithm is going to work correctly after any number of iterations.
Want to become a software engineer at Google? You can, like thousands of our students. You just need to learn from those who've already cleared FANG interviews. At Interview Kickstart, our interview prep courses are developed and taught live by 150 plus instructors from Tier 1 companies like Google and Facebook. Our courses are tailored to help you crack software engineering domain interviews, including back-end, full stack, machine learning, embedded systems, data science, and more. To learn more, book your free webinar slot today